Hi there. Today we are looking at inverse functions. So we are going to do all things inverses here. Lots of different things that deal with inverse functions. Let's begin with why maybe you'd want to have an inverse function. And so here's a nice formula for converting Fahrenheit temperatures to Celsius. And so let's say that you're traveling abroad, and of course everything else in other countries is Celsius. We use Fahrenheit in the United States. So when you see what the daily temperature is, oh, it's 75 degrees Celsius. I'm not very good with Celsius, so I'm not sure. Is that a good day? Nice day? What is that? Okay, so then what we would have to do is we'd have to take this 75 degrees and plug it in for C and go solve for F. And so it would be something like this. All right, so I'd have 75 equals 5/9 F minus 32. I'd take both sides, and you could distribute the 5/9. I'd be more inclined to take everything times 9/5. That crosses off. Whatever 9/5, let me grab my calculator here. 9/5 of 75 is a 135. That actually came out nice for us. Oh, I guess I could have done that, but whatever. Okay, 135 equals F minus 32. Add 32. Oh, okay, so 135 plus 32, that's 167 degrees Fahrenheit. That'd be a pretty warm day. So here's the thing, though. That's the conversion. Now, every time I have a Celsius measurement, I'm going to have to run through this algebra to figure out the Fahrenheit. And I would do it over and over. And the thing is it'd be nice if I had a different formula. What I'd really like to have is the inverse formula, the one that converts Celsius into Fahrenheit. And so you notice that this is the formula that converts the other direction. So instead of subtracting that 32, we're adding the 32. Instead of multiplying by a 5/9, we're multiplying by a 9/5. So what you'll find is that inverse functions have operations that undo each other. But the order that they undo them is important, so you'd have to be really careful with just changing pluses to minuses and so forth. Okay, so that's why we want inverses. So now let's take some time to actually look at how to find them and what to do with them. Okay, so the first topic that we're going to look at is verifying that two functions are inverses of one another. So this would be if I have two functions given to me, how do I tell if they are inverses or not? Okay, so what you're going to do, since inverses undo each other, if you just do composite functions, if you did f of g of x, what you would find is all the operations undo each other. And what would happen is you would get the exact same thing if you went the other way, if you did g of f of x. And both times, everything should cancel out until all you have left is x. Okay, so this is what you need to know. To verify two functions are inverses, you're going to do f of g of x, you're going to do g of f of x, and you're going to show me both times that you get x. Now, remember, you're verifying it, so it's really about the proof in your work showing me how this happened, not just saying yes or no. So let's try one. These are my two functions, f of x and g of x. So what I'm going to start off and do is I'm going to do f of g of x. So that means take the g function, plug it in for x in the f function. So I'm going to end up with 2, and instead of an x, I'm going to have a 1/2 x minus 2, and then that plus 4. Okay, and then I just go do the algebra on it. Distribute the 2. 2 times 1/2 is just 1x, minus 4 plus 4. The 4's cancel. All I have left is x. Okay, so that's what I wanted to have happen. Then I come over here and I do g of f of x. So take the f function and plug it in for x in the g function. So I'm going to have 1/2, plug in f of x, and then go do the algebra. So if you distribute 1/2, 1/2 times 2 is 1x, half of 4 is 2, minus 2, the 2's cancel, all I have left is x. So that's my verification. There's no real shortcut to doing that. If they want you to verify it or prove that they're inverses, it's all in showing that work to see how everything cancels out and you end up with x both times. Okay, the second topic we're going to look at is how do you find inverses algebraically. So if they give you a function and just one function and they want you to find the inverse of it. Now this is this thing that you probably have done before in Algebra 2 where you basically are just going to switch your x and y. So we start off, they give us a function. Remember f of x is really just y. And so what you do is you take that function and you switch the x and y around and then go get y back by itself. So in this case, to get that y by itself, I'm going to subtract 8. So then I'm going to have x minus 8 equals 3y, and then divide everything by 3. So I end up with a y equals x minus 8 over 3. Oops, that's a minus sign. Sorry, I was trying to make that bigger. Okay, so the notation that you should be using, once you have found the inverse, this is the notation for inverse. It's not the f function, it's the inverse of f. And we put a little -1 up there as notation for that. So your final answer should come back and say the inverse of f is x minus 8 over 3. Okay, so one more time. To find that inverse, you switch the x and y, then go get y by itself. Make sure your final answer has this nice notation. Okay, here's the next thing. It says, does the function have an inverse? Meaning, is the inverse a function? And if so, find it. Okay, so in this particular textbook, it's a little bit vague. It says, does it have an inverse? Okay, so their meaning by that is, when it says, does it have an inverse, does it have an inverse function? Meaning it has to be a function. So let's just practice finding those inverses a couple times. So on f of x, remember you're going to switch your x and y. So now it's an x equals 4y cubed minus 2. Now go get y by itself. Add the 2. Divide by the 4. So I have x plus 2 over 4 equals y cubed. To undo the cubing, I cube root both sides. And so now I have the y by itself. I've got the inverse. So my inverse function would be the cube root of x plus 2 over 4. Okay, so you try this next one. I want you to pause the video, go find the inverse on this next one. Okay, is this what you got? Go ahead and check your answer. Did you catch that plus or minus? That's a common mistake that we forget to put that plus or minus there, but that's important that you include that as part of your answer. Don't worry about this being a negative. Some people think that's, oh, wait, you can't have a negative under there. Well, that negative might go away depending on what your numerator ends up being, so that's not an issue. Okay, here's the next topic that we're going to discuss with inverses, and it has to do with just being able to look at a graph and figure out some things about the inverse. So we know from previous classes that you can do the vertical line test to determine if a graph is a function. Okay, so I put these two problems down here. If you look at this first one, y equals 4x cubed minus 2. Okay, if you'll recall from an earlier lesson that this is just a cubic, it's that little wave, it's going to get stretched, it's going to move down to, it's going to look something like this. Okay, that would pass a vertical line test. Now we haven't talked about a cube root graph, but it actually just looks something like this. That's kind of a parent graph of it. It's going to have some shifting and stuff going on, but that's the gist of a cube root graph. Now if you'll notice, this original problem, this passes a vertical line test. and so does its inverse. Okay, let's look at the second problem we did though. If you look at this first example, if you were to graph that thing, that's a parabola, and it's switched around a little bit. Normally this would be in the front and this would be a +5 on the back. So what it is it's an upside down parabola. It's stretched skinny, and then we got this +5 that would be out here, so it'd go up 5. So it would look something like this. All right, on this bottom one, this is a square root graph. Okay, so remember what a square root graph looks like, and it's going to have some motion going on with it also, but typically your parent square root graph looks like this. That should have hit the origin, but it's a sideways parabola. Now, we didn't really talk about it at the time, but what do you think this plus or minus is going to do to that graph? Well, this would be just a square root without the plus or minus. You throw the minus on there, it gives you the bottom half of that sideways parabola. Now, if you look at your vertical line test, this function definitely passes a vertical line test. However, this function would not. So this, though we went and found it all fine and dandy and got the inverse, remember what your textbook is going to say is, does it have an inverse? And what it means is its inverse a function? So what you should write on a problem like this is you'd say, no, its inverse is not a function. All right, so now let's look for a shortcut, because we went to a lot of work on that to find that, only to have to come back and say, oh, never mind, it's not really going to work. Okay, so we're familiar with the vertical line test. Now, ignoring these two things that we had already found, what we're doing is we're going to look at the originals. And I'm going to say, does it pass a vertical line test? Yes, it does. But here's the deal. Since you just switched your x and y to find your inverse, you actually can look at this original one and you can use what we call a horizontal line test to determine if its inverse is a function without ever having to actually find it. So let's look at this original problem. If I knew it was a 4x cubed and I knew kind of what that was going to look like, I could do a vertical line test on it. Even if I don't have to graph it perfectly, it's just a cubic. Yes, a cubic passes a vertical line test. Does a cubic pass a horizontal line test? Yes, it does. So that would tell me, all right, let's go find the inverse, because the inverse is going to end up being a function since this passed a horizontal line test. Okay, let's go to the second problem. You would look at this and pretend you haven't found the inverse yet, and you'd say, oh wait, this is just going to be a parabola. Yeah, it's upside down. It's moved around a little bit. But a parabola passes a vertical line test. So I know that it's going to be a function. And then I would say, will its inverse be a function? So I'm going to do a horizontal line test. And I'm going to say, oh, wait a second. That is not going to pass a horizontal line test. So its inverse will not be a function. So I really wouldn't even go to all this work. I can tell right up front that its inverse would not be a function because its graph would not pass a horizontal line test. Okay, so you do the vertical line test and the horizontal line test on the original function. You're not doing it on the inverse. By that time, you should have already decided it's either going to work or not work. Okay, still looking at these graphs graphically. What I want you to recognize, and we can look at them on a graphing calculator, but sometimes that's not ideal because it's a little bit deceiving looking on. It's just not squared up nicely. So I'm going to throw a graph in here that shows these two graphs graphed on the same screen. Okay, so I brought in this graph. This red graph here is the cubic. That's your nice cubic graph. And the blue graph is the inverse graph, this function right here. When I put those both on the same screen and it's squared up nicely, if you'll notice, they are perfect reflections of one another over this y equals x, this basic parent linear equation. They reflect over that line perfectly. That will always be the case. Inverses will always reflect over the y equals x line. And that's something, if you have the graph of them, you can kind of tell if they're inverses that way. Now, that all has to do with the fact that you swapped your x's and your y's to find that inverse. It changes that graph nice symmetrically. Okay, which brings us to one more thing, and that's when you look at a table of inverses. So I told you, we're doing all things inverses. We're looking at them every which way we could. So you have these two equations again. I tried to stick with the same equations over and over, and what I want you to do is look at a table here. Let's just throw in some numbers. Let's put in, well, I don't know, let's put in a 0 for x. Okay, you plug 0 in for x, that's 0, you get -2 back. Let's put a 1 in for x. That's going to be 1 times 4 is 4 minus 2 is 2. Let's plug in a 2. So that'd be 2 cubed, that's 8, times 4, that's 32, minus 2, that's 30. And I could sit here and do point after point after point. Now I'm going to come over here and do the same thing with the inverse function. I'm going to plug something in for x and then see what I get back for y. Okay, this one's a little trickier. I'm doing a cube root. I'm going to end up with some pretty ugly numbers if I'm not real careful here. So I'm going to hand pick some x values that are going to make this come out nicely as a perfect cube. So then when I cube root it, it'll come out nice for a y value. So if I want this to be a perfect cube, we need to take a minute and think of what are my perfect cubes. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. I suppose if I really wanted to make my life easy, I could do 0 cubed is 0. I don't know. Okay, so those are all my perfect cubes. So what I'm going to do is I'm going to try to make that happen inside here. Okay, so let's work on, well, I guess let's work on the 0. Could we make the 0 happen? So what do I need x to be? And I'm just doing this mentally. What do I need x to be for this to end up being a 0 under here? Well, I need my numerator to equal 0. So for that to happen, I'm going to have my x be -2. And then I'll end up with 0 over 4. That's 0. Cube root of 0 is 0. Okay, and let's try this 1. What do I need to do to make it be a 1 under here? Well, I need the numerator to be a 4. So I have 4 over 4. So for this to equal 4, x is going to have to be 2. If x is 2, then I end up with 4 over 4. That's 1. And the cube root of 1 is 1. Okay, let's try one more here. Let's do the 8. So I want to somehow make this be 8. So it'll cube root nicely. All right, I've got to take a number and divide by 4 and have it equal 8. So I need this to be 32. 32 divided by 4 would get me an 8. So that means x needs to be 30. So I'll put 30 in for x. Then that's 32 over 4. That's 8. And the cube root of 8 is 2. Okay, so now that I've done this, take a minute and compare these two tables. What do you notice happened? The x's and y's just switched. Okay, well, that should make sense because I switched my x's and y's to create this function in the first place. So that's another feature of inverses. Their tables will have their x's and y's swap. Okay, so last thing, we've talked lots about different features of inverses. I just thought it'd be good to have a quick summary page, and maybe you need to put this in your notes as kind of a summarization of everything that we talked about. So here we go. First of all, if you're looking to find an inverse, they give you a function, they say go find the inverse. Okay, then you're going to swap your x and y and resolve it for y. And make sure you use that nice notation. All right, if you're looking at a table, you should find that your x's and y's swap in the function table versus its inverse table. Okay. If you have two functions and they just want you to verify if they're inverses. That's when you do the two composite functions. You do it both ways, and you hope that everything cancels out and you just get x both times. The verification, the work, that's what I'm looking for on problems like that. All right. If a graph passes a vertical line test, then it will be a function. If it also passes a horizontal line test, then its inverse will be a function. And remember, you do both of those tests on the original problem. And the last thing, what we just talked about there earlier, inverses are reflections of each other over the y equals x line. So if you're looking at their graphs, you can tell they're inverses that way. All right, lots of stuff about inverses. Good luck.